We learned about the 3 different gas laws. The last couple of days we've been talking about the ideal gas law, and now my computer's going to try to update, and I don't want it to. So today we're going to learn about Dalton's law, which basically deals with just pressure, and then we're also going to continue to use the ideal gas law, PV equals nRT, to apply different types of problems. We're going to do a little bit of stoichiometry. We're going to do a little bit of mole ratios. You're going to have to balance equations again today, but I think most of them I balanced for you. All right, so let's start off with gases and stoichiometry. First of all, reactions happen in... Why is my computer? I need to just throw it against the wall and see if it works then. There we go. Reactions happen in moles. That's why when we write balanced chemical equations, we balance them using coefficients, and those coefficients are telling us what? The mole ratios, right? So it takes 2 moles of this gas plus 1 mole of this gas to produce 3 moles of our product. So whatever the mole ratios are. Okay, so at standard temperature and pressure, which is again 0 degrees Celsius or 273 Kelvin in 1 atmosphere, 1 mole of gas occupies 22.4 liters. But why is this not necessarily a good thing? Why is STP not necessarily a good thing? The majority, unless we are at exact sea level, we're not going to be under 1 atmosphere. Okay? We might be really close, but we're not going to be exactly at 1 atmosphere. And 0 degrees Celsius, not necessarily going to be at that in normal conditions. Okay, that's not going to happen naturally. So if we are not at standard temperature and pressure, we use the ideal gas law to calculate the moles of the reactant or the volume of the product, or vice versa, whichever we are solving for, whichever one we don't have. Yeah, it's cold. It's 19 degrees. Look how red your legs are. Yeah, it's really cold outside. All right. So let's do an example problem. It uses PV equals nRT, but we're going to change the conditions around a little bit and see how we go about doing that. So, for example number 1, it says mercury can be produced by the following reaction. We have mercury oxide, and it will yield our liquid mercury, which everyone knows what liquid mercury looks like, and oxygen gas. Now, you see something over the arrow. What is that telling you? Heat is being added to make the reaction happen a little bit faster. Is mercury oxide going to break down all by itself? No, so we're going to have to add something to it. So are we going to change standard temperature and pressure? Yes. This will not happen at STP. It'll only happen if you add heat to it. So, what volume of oxygen gas can be produced from 4.10 grams of mercury 2 oxide at, first of all, standard temperature and pressure? But we already know that's not going to work because we have to add heat. So then we're going to raise the temperature to 400 degrees Celsius to see what happens to the volume. And then what are we going to do to the pressure? 744, huh? We're going to lower the pressure and see if that's going to affect the volume very much. We're going to see which one of these factors affects it more. So, first of all, mole ratios. We are given... What do you think we should do before we can do mole ratios? Balance the equation. So first of all, we have to balance this equation. So we see 1 mercury, 1 oxygen on the left, 1 mercury on the right, but 2 oxygens on the right. So first off, we have to balance oxygens. Add a 2 right here. And then that messes up our mercury, so then we add a 2 right there. Now we're all nice and pretty and balanced. Yay, right? All right. The next thing that I'm going to do is I am going to convert 4.10 grams. I'm just going to go ahead and put that into moles so that when I start using PV equals nRT, it is... When I start using PV equals nRT, I'm already in moles. That way, once I start doing all my conversions, I don't have to go, oh wait, grams, moles. So I'm just going to go ahead and put that into moles right away. So how do I convert 4.1? And I actually, for those of you writing on notes, I did the mole conversion underneath example 1, but before A, B, C, so I wouldn't run out of room. Okay, So how do I convert 4.10 grams of HGO? I need the molar mass. Okay, so mercury is 200, oxygen 16, so the molar mass is 216, and that is 1 mole. But let's look at the question. Before we go ahead and hit equals, let's look at the question again. It says, what volume of oxygen, not mercury oxide? So we need to do one more step, right? Because we're not going to use PV equals nRT for the moles of mercury oxide because we don't want the moles of mercury oxide. It's asking for oxygen. So we need to go one step further, and we need to use our balanced chemical equation, and we're going to see that we need 2 moles of mercury oxide for 1 mole of oxygen. Now, can I hit equals in my calculator? Yes. So I'm going to put this in my calculator, and I need to write an answer down with significant figures in mind. So how many do I get to keep? 3. So my answer is going to be, don't you guys like how I do the calculations for you? 0.00949 moles of oxygen. Okay, put a circle around that because we're going to be using that for A, B, and C. That way you know exactly where it's at on your notes. Okay, and I'm actually going to have to hit erase, so you guys are going to have to remind me what this number is here in just a minute, okay? All right, so now let's start answering the problem. So let's start with A. A is wanting to know what the volume is going to be under standard temperature and pressure. And let's actually, to make our math just a little bit easier, let's go ahead and move pressure to the other side. So PV equals nRT, correct? But since we're solving for volume each time, let's just go ahead and put P on the other side. That way we don't have to we can write our problems out really easily. Right, so if we move P to the other side, that makes it V equals nRT over P. Since we're solving for volume every single time, there's no sense in us rearranging the equation every time, right? So now let's do A. So we need to solve for the volume. Okay, we know our equation. N is what? Moles. We just did stoichiometry, so what is our mole number? And I am not going to write my units in because I will run out of room. Okay, but then we need our R. What's our R? Okay, and that is in liters, atmospheres over moles times Kelvin. So as long as we are always in those units, which, like I said yesterday, it kind of becomes a habit after a while, we will not mess up our R. Then we need a temperature. Standard temperature is 0 degrees Celsius, 273 Kelvin. And then we're going to divide by our pressure, which is 1, which is why I wanted to rearrange the equation. So now we just have to put the top part of this in our calculator. How many significant figures do I keep? 3, because again, the only one we're really worried about is 4.10, correct? All right, so then after I put all this in my calculator, I'm going to get a volume of 0.213 liters. So under standard temperature and pressure, we are going to produce 2.13 liters of oxygen gas. Are we going to produce very much oxygen? No. About a quarter of a 2-liter bottle of soda, right? A little less than a quarter. Huh?
Okay, so I understand why, but putting in the equation, why would you not just take from the mole so like 1 mole is 22.4 liters?
Because we're not factoring in our rate. Because if we just use stoichiometry, we're not going to factor in this rate. And remember, R is a constant that all gases do when they're under standard temperature and pressure. So we could do stoichiometry, and we would probably get pretty close to this answer, but we wouldn't be factoring in the rate. Okay? All right, so now let's look at B. B says, well, this reaction is obviously not going to take place under standard temperature and pressure. As we read the equation, we have to add heat. So automatically that tells you we're going to have to change at least the temperature, right? So this time around, we're going to use the exact same equation. We are going to be using volume is equal to nRT over pressure. But this time we're not under standard temperature, but we're going to do the exact same process. Our moles was 0.00949. Our rate is still the same. Our temperature is changing this time. It's at 400 degrees Celsius, which is what, Kelvin? 673. And we're going to assume our pressure did not change and it's still under 1 atmosphere because it didn't mention that we were changing the pressure. So again, you just have to put that top part in our calculator, correct? And we should get an answer of how many significant figures first? 3, 5, 2, 4 liters. So what's happening to our volume as we increase the temperature? It's increasing from 0.2 to 0.5. So it's a little more than doubling, correct? So what does that tell you about what does that tell you about changing the temperature? It makes their volume go up, which is telling you what about the reaction? The reaction is happening faster, or it's happening more, which makes sense because it says heat is a catalyst. So if we increase the heat, the reaction should take place at a faster rate, correct? Which our math just proved to us, right? All right, so now let's try C, and I'm actually not going to delete everything because we're only changing one number, right? So I can leave everything the same, except this time, what are we changing? We're changing the pressure this time around, not the temperature. Temperature, we're going to assume, is at standard temperature. This time, we are changing 740 torr. We need it to be in ATMs, so 740 torrs. To put that in ATMs, we have to divide by 760, correct? Which I went ahead and did so that we can put this in our calculator a little bit easier. Gives us 0.974 ATM. So now we can put this in our calculator just a little bit easier, right? So how many significant figures this go around? 2. So after I put all of this fun stuff in my calculator, I'm going to get an answer of 0.22 liters. So, what does this tell us about the effect of pressure on this reaction? Think about the first answer, wasn't it 0.21? This one's 0.22. So what is it telling you about pressure? It doesn't have that big of an effect on it than the temperature did. However, we did raise the temperature by 400 degrees and we only changed the pressure by 20 torrs. So we also didn't change the pressure by such a significant number as we did temperature. But still, we changed the pressure. It didn't really do a whole lot to the volume. All right, so how do we feel about using stoichiometry? All right, so I'm going to get you started on example number 2. But like I said, you guys are going to do example 2, part B, and then example 3 and 4 as homework tonight. So I'm going to get you started on example 2, though. Okay, so example 2 is using sodium hydrogen carbonate, or it's also called sodium bicarbonate. This is actually what I used last year when we did tie-dye. This is what I soak your t-shirts in to break the bonds. So it's a very strong basic solution. Okay. All right, so part A says, calculate the mass of sodium hydrogen carbonate necessary to produce 2.87 liters of carbon dioxide at 25 degrees Celsius and 2 atmospheres. These problems are pretty wordy, correct? So we really need to honestly just come up with a way to break down what it's actually asking us for. So what is it asking us for? It's asking us for mass. So to use PV equals nRT, as soon as I see mass, what is happening in my head? We're going to have to do some sort of mole conversion, right? Because we can't use PV equals nRT to get grams. So we're going to have to get moles and then go to grams. So before we even start this problem, let's just make sure our equation is balanced in case we're going to have to do some stoichiometry in a minute. So, is my equation balanced? Yes. So luckily for us, it's 1-to-1. Everything's good. So, first off, we need to figure out the moles, correct? Do I have P? Do I have V? Do I have N? No, that's what we're solving for. Do I know what R is? Do I have T? Yes, so I can use PV equals nRT. And we're going to solve for N. So my pressure is 2 atmospheres. My volume is 2.87 liters. My N is what we're solving for. My R, 0.08 2, 1, right? Yes. And then this is in atmospheres, liters, moles, Kelvin. Okay, our temperature was given to us as 25 degrees Celsius, but we have to add 273. So what's my actual Kelvin? 298. And now I'm ready to solve for N, correct? Just double check really quick. All our units are good? We have K, we have L, we have atmospheres. We're good to go. All right. So how many significant figures do I get to keep? 2, because 25 degrees Celsius only has 2. So I'm going to round my answer as 0.24 moles. So in this reaction, under these conditions, I am going to produce 0.24 moles of carbon dioxide, right? Because 2.87 liters of carbon dioxide at these conditions. So I'm producing 0.24 moles of carbon dioxide. Isn't the problem asking us for sodium hydrogen carbonate? And this just gave us moles of carbon dioxide. So what is flashing in your head now? Stoichiometry. So I'm going to erase really quick. Somebody's going to have to tell me that number again in just a second. So now I need to do some stoichiometry, and I'm going to start with the answer I just got. So I'm going to start with 0.24 moles of CO2. We don't want CO2. We want hydrogen carbonate, correct? So we look at our equation. Luckily for us, everything is a 1-to-1 ratio, but you still have to write it down because I can't read your mind, right? 1 mole of CO2 is going to produce 1 mole, and I'm going to be lazy, and I'm going to say NC, because I don't want to write sodium hydrogen carbonate over and over and over again, right? So then we need a mole ratio, right? Because it's asking for mass, it's not asking for moles. So 1 mole of our sodium hydrogen carbonate is going to give us, and I went ahead and did it for you, is going to be 84.01 grams. Moles cancels, we're left with grams. So now all I have to do is the math. So I'm going to get an answer of 19.7 grams. Is that good for significant figure land? No, so I have to round that, which brings us to 20. So how do I write 20 and maintain 2? Don't forget the decimal. So 20 grams of sodium hydrogen carbonate. So basically we are taking our ideal gas law and we are applying it to stoichiometry. Stoichiometry went away for like a unit, now it's back, right? But by this point you guys probably like stoichiometry. Alright, so like I said, you guys are going to finish part B and you're going to do example 3. Maybe. And 4. Alright, so flip over your notes page and let's start talking about Dalton's law. This is the new information for today. Dalton's law involves partial pressure. So Dalton's law says that the total pressure in a container is the sum of the pressure each gas would exert if it were alone in the container. So basically he says that in your soda bottle, if it is sealed, there are lots of different gases in a soda bottle, right? He says that all you have to do is add up their partial pressures and it's going to equal the total. So if we know the total pressure, we should be able to figure out the other ones. Okay? So the total pressure is the sum of all of your partial pressures. Partial pressure, like I said in the soda bottle, each gas is exerting a pressure. You add all of their individual pressures up to get at the total. So each one is their partial. So partial pressure is the pressure exerted by a particular component in a mixture of gases. So each gas, again, is going to exert its own specific pressure based on how big it is, based on how fast it's moving. And we term these their partial pressures. So, to get your total pressure, you just physically add the pressure of one gas, the pressure of the second gas, the pressure of the third gas, so on and so forth. Yes. Yes, this is the same Dalton. He was very important to chemistry. Okay, so we can also, but maybe we don't know, maybe we know the total pressure, but we don't know the pressure each gas is exerting. So we could rearrange the ideal gas law, and we could physically say, in order to get the pressure of each thing, the volume's not going to change in a container, right? The gases are all under the same volume. The rate's not going to change. The temperature is all the same, right? The only thing that's going to be different from each gas is how much of each gas you have, right? So we can use this law. And I have it. Oh, there it is. So basically, if you don't know each of the partial pressures, you can just rearrange ideal gas law and do the ideal gas law of the first gas plus the ideal gas law of the second gas plus the ideal gas law of the third gas. Honestly, it just depends on what you're given in the problem. There's lots of ways to rearrange an equation. But if all of our temperatures are the same, and all of our rates are the same, and all of our volumes are the same, which is honestly what's going to be true, right? If you're in a container, aren't they going to be under the same pressure? Aren't they going to be under the same temperature? Yes. So if all of that is the same, why do the math every single time? Do your moles, add all your moles together, and then multiply your moles by that. There's no sense in doing that math over and over and over again if everything stays the same. It's kind of like pulling out your like variables in front of an equation or in front of a parentheses in math class, right? Pull out all your x's. So, rearrange it one more time. Our total pressure should equal our moles times those constants. So, this is the lab that we are going to do on Tuesday. Basically, what we are going to do, we're not going to use zinc because zinc didn't work so well last time we used it. We're going to use magnesium because we all know that magnesium and hydrochloric acid react, because if you guys remember last year, didn't we do that experiment? Mm-hmm. And when we did balancing equations and chemical reactions back in regular chemistry, magnesium and hydrochloric acid react really easily. So this is actually what we're going to do. We're going to set up this apparatus that you see right here, which is the part I'm a little nervous about. I've never done it before, and it seems like there's a lot of places for error, right? So basically, we have a container that is inverted or upside down. We're going to fill it completely with water, and we're going to invert it into another sort of like a tub that's also filled with water. And then over here in a test tube is where we're going to have our magnesium and our hydrochloric acid reacting. And if you notice, it's stopped up here. So all of the gas that's being produced has to travel through this tube and into the inverted container. And as it's producing gas, the gas is going to travel through the tube, and it's going to push up because gases float on top of water, right? And it's going to bubble, and as it starts to fill this container, what's going to happen to the water? The water is going to be displaced into the tub, so we should be able to see how much water is being displaced. Therefore, we can tell how much volume of gas we are getting, right? So this seems like a cool experiment. I've never done it before. We're going to give it a shot. We're going to see what happens. Yes, Monica. No, because it's filled with water. And so once the water levels reach equilibrium, yes. But until this water is lower than the water in the tub, then no, it's going to be heavier and it's going to stay down. Does that make sense? Once there's no more water, then yes, it'll jump up. But we're going to make sure that doesn't happen. We're going to put it in a pretty big bin so that as the water comes out, it's not going to. So this should be interesting. Not really sure how we're going to do this, but we're going to give it a shot. Okay? All right, so next week I'm going to do example 5. It's actually not even in your notes. I'm going to do this before we do the lab, so it's actually not even in your notes, so we're going to skip it for right now. And on your notes, the next thing, I should have rearranged this before I hit print, but I didn't, so I forgot. I'm sorry. But skip mole fraction, go down to vapor pressure, and we're going to come back to mole fraction in a second. I moved around the slides a little bit to make the flow work, and I forgot to rearrange it on the notes. So anyhow, let's start talking about vapor pressure, because that's what we were just talking about in that lab that we're going to do next week. we are going to collect a gas over water. When we do this a lot because the pressure inside and the pressure outside will equalize themselves, and so it actually happens on its own. So what we do is we get our total pressure, which is going to be atmospheric pressure, which we can use an instrument to determine what the atmospheric pressure is. And it is going to be equal to the gas that you're producing plus the pressure of water. Because as we do that experiment, as the gas is filtering through the water, it's going to excite some of the water atoms, and it's going to knock them into their vapor phase. So it's not going to be solely the gas. It's going to be the majority of the gas, but along the way we are going to throw some water in the vapor. So to get our total pressure in that type of experiment, it's going to be the partial pressure of our gas plus the partial pressure of H2O. However, if for some reason the equalization does not occur, then we also have to account for the pressure difference, which is again why we have the H2O there. We can look up these standard values in a textbook, and we can throw in the value, and then we can solve for P just by doing subtraction. Okay. Did I go too fast? Sorry. There we go. So again, the standard values, we know what temperature the room's in, so if we're doing this experiment, we can look up the temperature that the reaction's happening in, then we can figure out approximately how much water vapor is going to be in our solution, and then we can just do a subtraction problem. So let's do, it's actually example 7 on your notes. Again, I just didn't edit this like I should have. N2O can be produced by the following reaction. So if we take ammonium nitrate, some little test on if you guys remember your polyatomic ions, right? We take ammonium nitrate, we add a little bit of heat as a catalyst, we are going to get nitrogen dioxide as a gas, and we're going to get a little bit of water as a liquid. So the question says, what volume of N2O collected over water at a partial pressure of 94 kPa at 22 degrees Celsius can be produced from 2.6 grams of ammonium nitrate? These word problems get a little crazy, right? Yes. All right, so the problem is written correctly. The balanced equation is not written correctly. So this is the right answer. Whew. This is correct. No, wait. This is wrong. So we're going to put not NO2. It's going to be N2O. Now everything is balanced. Everything is nice and happy. 1 to 1 to 2 ratio. Yay. So this is wrong, and this is wrong. Okay? All right, so now let's start. Now that we figured that out, we are still looking for the volume of our N2O, correct? That's what we're ultimately solving for. So we're going to have to be using probably PV equals nRT along the way, right? But we don't know the pressure of the nitrogen or the dinitrogen oxide, right? We don't know that. So we have to figure that out. Do we know the total pressure? Yes, it tells you that the total pressure is 94 kPa. It then tells you that the partial pressure of water at 22 degrees Celsius is 21 torrs. So we're going to do a really, really easy math problem to figure out the pressure of our nitrogen. Yes? Okay, so again, we're going to use our total pressure. It's going to equal to our pressure of our nitrogen plus the pressure of our water vapor, which they told us. So we have 94 kPa. We have 21 torrs. What unit do we like so that we can use our ATM? So, I mean, honestly, if you want to use kPa, you can convert towards kPa. You can look up a different R value, but I like atmospheres, so I'm going to convert them both to atmospheres. So, 94 kPa times 1 ATM over 101.3 kPa, and I get 0.928 ATMs. But I also don't like torrs, right? So 21 torrs times 1 atmosphere over 760 torrs And you're not going to be able to see my answer in just a second. But that is going to give me 0.0276 ATMs. So now we're all in ATMs. That way we can use our PV equals nRT in a second. No problems, right? So now we just have to plug in. We know our total pressure was the 94 kPa, so our total pressure was the now 0.928. The pressure of our N2O is what we are solving for. We found the pressure of our water vapor to be 0.0276. So now we honestly just have to do a little bit of subtraction, right? So the pressure of our N2O is going to be 0.9. How many significant figures? 2 atmospheres. Looks like a lot of work, but it's really not. It's really just a subtraction. The only hard part about this was all the converting, correct? So now we have our partial pressure of N2O. What's the problem? Are we done? No. What's now? We don't want the partial pressure of nitrogen, do we? We want the volume. So, I'll have to erase because I ran out of room. Alright, so now we need to solve for volume. So, we rearranged our equation a second ago, so let's just keep using that. Our volume of PV equals nRT is going to be nRT over P. Whoa. We can't have grams of NH4NO3, can we? Nope, we have to have grams. So I skipped a step. 2.6 grams. And I'm definitely not writing that over and over again. Ammonium nitrate. We need a mole to mole ratio, right? So 1 mole of ammonium nitrate is going to equal 80.05 grams of ammonium nitrate. But we don't even want moles of ammonium nitrate, do we? What do we want? We want moles of N2O. So 1 mole of ammonium nitrate is equal to 1 mole of N2O, which makes our math a little bit easier, but you still have to write it down, right? Which is going to give us a mole value of 0.0325 moles of N2O. Okay, now can I use PV equals nRT? Yes. Okay. A lot of work just to get to our ideal gas law, huh? All right. Volume is equal to our N, which we just found was 0.0325. Our rate, 0.0821. Our temperature, 22 degrees Celsius, is 295. And our pressure that we found the first step is 0.90. Whole bunch of math, right? And we should get an answer of 0.87 liters. So if we do this reaction and we have 2.6 grams of our reactant, we are going to produce 0.87 liters. All right, so now, yes, because it's specifically asking you for nitrogen N2O. It's not asking you for the total pressure of the gas. All right, so really quick, we're going to try, the next part is really easy. Jump back up to the mole fraction. We have 5 minutes. I think we can do it. The mole fraction is a dimensionless number that expresses the ratio of moles of a component substance to the total moles in a mixture. Dimensionless basically means no unit. Okay, there is no unit for the mole fraction. It's honestly just a ratio of your moles. Okay, so to do this, first of all, it's represented with the Greek letter chi, which was typed incorrectly on your paper. It's kind of like a funky looking, I I think it's chi technically. I read it as chi because I have a straight line. But anyhow, it has the funky looking X, right? Okay, so rewrite that on your notes. And to solve for this, you honestly just take the mole of your partial gas and you divide it by the moles of your total. Or, since moles and pressure are directly related, you can also just take the pressure of your whatever you're dealing with divided by the pressure of the total. So, let's do an example. The partial pressure of nitrogen in air is 592 torrs. The air pressure is 750 torrs. What is the mole fraction of nitrogen? Do we have to do any converting here? No. Easy, easy, easy math. So, again, there's our mole fraction symbol. We're going to take the pressure of our gas, and we're going to divide it by the pressure of our total. So, we're going to take 592 divided by 752. Our units automatically cancel out, right? And we're going to be left with 0.787. No units because it's dimensionless. Well, this is talking about the partial pressure of nitrogen in air. Well, we all, back in chemistry, you memorized that our air is made up of 80% nitrogen. Is it actually 80%? It's 78.7%, but pretty close, right? So this is how we know what the air is made up around us. This is how we know. This is how we figure out what composition the air is. Okay? All right, so I'm adding, let's try to get through example 8. If we don't get through example 8, it's homework too, but it's just as easy. So it says, what is the partial pressure of nitrogen in the container holding the air if it is compressed to 5.25, right? So we started off at 752 torrs. It was initially that. It is then going to get compressed to 525 atmospheres. Uh-oh. Torrs atmospheres. We can't compare apples and oranges. We have to compare apples to apples. So we can either convert torrs to atmospheres to torrs. What do you think I did? Atmospheres, it's just a habit. So if I convert this, it's going to be, how did I convert this to atmospheres? Divided by 760. That makes sense. 752 is not that much smaller than 760. So then to do my mole fraction, you do what? You're going to take this number, hold on just a second, 989, divided by the total, 5.25, and we're going to get 0.148. So if our container is compressed, it's no longer going to be 78%, it's going to be 14.8, so 15%. All right, don't forget about those example problems as your homework.